Great. We are talking about metric spaces. And I want to get into today the relationship between metric spaces and topological spaces. Remember, a metric space is a set X with a metric, which is a function, x cross x to R. And the metric satisfies three properties. It is positive definite and symmetric, and it satisfies the triangle inequality. So the positive definite property is that distance from x to y is greater than or equal to 0, and distance from x to y equals 0 implies x equal y. That's the positive definite property. The next property was the symmetric. That's maybe the simplest one. Simplest one, maybe you should write it first, although nobody writes it first. I don't know why. And then the last property is the triangle inequality, which is typically the most complicated one. That's distance x to y plus distance y to z is greater or equal to distance from x to z. All right. If a function satisfies those three properties, this is meant to be something like a distance function. If it satisfies those three properties, then it's called a metric. And we had several examples of different metrics last time on R2. There is the standard metric, which is the ordinary distance between 2 points in R2. That's called the standard metric or the Euclidean metric. And then there were a couple others that we talked about. The taxicab metric, remember that's the one where you measure the horizontal distance and add it to the vertical distance. This was the dt of 2 points. We usually were using p's and q's in R2. The definition of that was p1 minus q1 plus p2 minus q2. That's the distance in the x direction plus the distance in the y direction. That's called the taxicab metric, because that's sort of the distance between the points if you are constrained to only moving horizontally and vertically. All right. I thought we should talk about one more example of a metric on, like a weirder metric on a space which is weird. So last time we only really talked about R and R2, although these metrics on R2 that we talked about, you can do them all in Rn in higher dimensions. But how about a set which doesn't really look like Rn at all? You can still talk about metrics in totally different settings. So here's just one last example, and then we'll talk about what this has to do with topological spaces. So for a closed interval A to B, let C of A to B be the set of all, let's say, continuous functions that go A to B to R. So this is the set of all real valued functions whose domain is the closed interval A to B. So that thing, C of AB, this is sometimes called a function space. It's a set of functions, right? A typical function in here is, something that looks like, if here's A to B, something like that. That's what one of these things looks like. So this is a space in which, like, the points are functions, all right? And you can measure the distance between two functions. Actually, there's many ways you could imagine to measure the distance between two functions. If I have like a f and a g, can you talk about how far away is the f from the g? It seems like that ought to be something that you can discuss. And actually, there are a few different ways to discuss it. Maybe I'll write another g. How about here's a g. That's a g, right? Both of those things here, f and g, are both elements of this function space. It's a set of functions, all right? What's the distance from f to g? You could think about how, what could you possibly do to measure a specific like numerical distance between f and g? There's a few different ways that you can do it. One of the most sensible ways, one way you could think of doing it is it's the, like you could just look at these vertical distances, say, and could you somehow use one of those vertical numbers to act like the distance from f to g? If you took, like, say, the closest they ever got and call that the distance, actually that is not a metric, because by that measure these two functions would have distance 0, because sometimes they actually do meet. Can anyone say, what's the problem if I said these two functions, they are distance 0 apart? Is that actually is not allowed if you're trying to do a metric. That would violate one of the three properties.
Violate the pos-def?
Yeah, the pos-def, the positive definite property, says that if the distance is 0, they have to actually be the same. And these are not the same. So their distance, however you want to define their distance, it can't be 0 in this case. One thing you could use is the maximum distance between them. Actually, that would be a metric on the space of functions. If you just look at all the individual vertical distances and just take the biggest one, that would actually make a metric. Here's another way, which is a little more interesting. We can define a metric like this. Distance, I'll write it down here. Distance from f to g is, how you like this, the integral from a to b of absolute value f of x minus g of x. It's maybe the only time I write the integral sign in this class. That is using as the distance, you just use the area. That's basically like the blue shaded in area. I didn't fully shade it in, but since I'm taking the integral of the absolute value, it means that I'll like either of these, where the f is on top or where the g is on top, they will both be measured as if they were positive area. And this will give you actually a very nice metric between two functions. All right, I don't want to get into the details, but this actually is a metric. It satisfies the three properties. So this is a metric. So remember, this is just a little notation. The way I would write this is like this. CAB, comma, D is a metric space. All right? Which means you can do, you know, metric type stuff in that set using the D. All right. I thought we should have at least one example of something that's more interesting than just distances in the plane or whatever. Any thoughts about that? Questions about that? Great. There are other ways you can measure the distance between two functions, but this is a common and popular one. All right. I would like to talk about what does all of this have to do with topological spaces. So I want to talk about metric spaces versus topological spaces. Because actually all of this, we defined everything without ever saying the word open set or anything like that. But metric spaces are, they kind of carry topological information inside of them also. So there is a standard way, actually, and this is sort of our goal for today, a standard way to convert, or maybe I will say, create a topology in a metric space. All right. If you have a metric, actually that tells you a standard way to say what is an open set and what is not an open set. And that will allow you to make a topology. So any metric space actually can be viewed as a topological space in this way that we're about to discuss. And actually I think everything that I say today is going to be more or less what you would have come up with on your own if I gave you more, if you had some time to think this through on your own and the motivation. How can we decide? So we need to create something like small neighborhoods using the metric somehow. So if I have, 2 points, x and y, and I don't already know how to make a neighborhood around x. All I have, though, is this function which tells me the distance from x to y. Actually, if you do have such a function, I think it does become clear how to sort of make up what do I mean by a neighborhood around x. I think what I mean by a neighborhood around x is just all of the points which are close to x using that metric, right? All the points that are within, some number of x, within 1 of x or within a half of x or something like that. You can define that using the metric, and that will allow you to do all of the things you want to do sort of in a topology. So this whole thing is based on little neighborhoods that look like this, and just like in topological spaces, we're going to call these, or just like in Rn, we've used this word before, we're going to call these the epsilon balls. And you can define these in any metric space. So we can define B of x comma epsilon is how they write it. This means the ball around x with radius epsilon. And this is defined to be all the points which are within distance epsilon from x. This I would write as something like all points y, such that distance from x to y is less than epsilon. All right? You can make this whole definition using only the metric. That's the point here. This is all of the other points which are within distance epsilon. So actually on this picture, the y is outside of this neighborhood, right? Or outside of the ball around x of a certain radius. All right, this here is called the open ball or actually around x of radius epsilon, or more commonly I would just call this the open epsilon ball. All right, the open ball around x of radius epsilon. I happen to be scrolling the I think I saw this on Twitter. They showed me this article about popular math-related baby names. I get these baby names articles. I'm not sure why. I think it's because I think they're so stupid that I read them, and then they send me more because I read it. But one of them, they suggested a great mathematical baby name for a boy is Radius, which I thought they all sounded ridiculous to me. Yeah. I think Epsilon was one of them too. They were all stupid. One of them was one of them was Truth. They're like, mathematics is all about truth, so Truth counts as a mathematical name. I don't know. Anyway, this is the open epsilon ball around x. All right, B of xe. Sometimes it's useful to talk about the closed epsilon ball around x. Anybody want to imagine? It's very similar to this, the definition. How would you change this just very slightly to make it something like closed? Now, I'm not, we haven't really said what open and closed means yet in this setting, but how would you change this to make it like a closed ball? This one's sort of open because it doesn't include its boundary points. The closed epsilon ball is typically written with the bar because we like to use the bar for closed things. How would you make it close? Close it up? There's a very simple way to do that. Just change a little something. Yeah.
Less than or equal to.
Yeah, just make it less than or equal to instead of straight up less than. Then you get sort of, it'll be just like this, only you will additionally get all the points right along the boundary. So this is distance x, y, less than or equal to epsilon. So sometimes it's helpful to talk about the closed epsilon ball. All right. Now these are, we want to eventually think of these as open sets and closed sets, like in the topological sense. Although for now, that's just like part of the name of those things. The balls will look different depending on what the metric you're using is. So the balls can look different in different metrics. Can we just let's try and think a little bit about what the balls will look like. Maybe I'll talk about the easy one. I'll let you guys think about the others. So let's talk about the standard metric in R2. If I have, say, what I want to know, like what does ball of x comma 1 look like? So if x is here, ball of x comma 1, that means all of the points which are distance 1 from x. Can anyone say, like as a shape, what does that look like in R2? Using the ordinary distance function, all of the points which are distance 1 from x. It's a circle, yeah. It's sort of the region bounded by a circle. So it is, I'll write this with a dotted line around the edges, everything in here. So this is, actually topologists are a little touchy about the language. This is called a disk. A circle means like the outer edge of a disk. So when a topologist says circle, they always mean that sort of thing that topologically looks like a line that goes back to itself. The word disk is what we use for the sort of inside region of a circle. Anyway, that's what it looks like. These are all the points which are distance 1 from x. 1 or less, right? Actually not 1, just less, right? All the points which are distance less than 1 from x. Maybe I would let you guys think about it, chat with your friends about it, strike up a conversation with a Julia. Can we talk about what does a ball look like in one of these other metrics? So the other metrics we had was the taxicab metric. Think about, if I have some x here, what does ball of x1, what's the shape of that using the taxicab metric? So I will just refresh your memory how you do the taxicab metric. If I have, say, x and y, you go like that, and you add together these the horizontal and the vertical distances. So maybe to get you started, this x is just going to get in my way. What if I just went straight out to the right by a distance of 1? Is that part of the 1 ball? I think it is. Well, actually, that would be right on the edge of the 1 ball. What if I went straight up by distance 1? Is that also part of the 1 ball? I think it is. So like this ball would include those 2 points. But actually, if you imagine, don't write this down, but if you imagine the circle, actually this point out here, that is not part of this ball using the taxicab metric, because for that point right there, the distance with the taxicab, the diagonal distance is 1, but with the taxi metric, it's more than 1, right? It's something like, is it root 2? I think, if you remember your unit circle. That's not important. It's more than 1, though. That's all that I care about. So actually, like these 2 points here, they actually are part of, at least they're part of the boundary of this ball, but not that. So you gotta think a little bit about, it's not the circle, right? I'm gonna erase, erase, erase. Okay, think about what does the shape actually look like. And then also I want you to think about the max metric. Remember, that's the one where if you have 2 points, you consider the horizontal and the vertical distance, and you always choose the one which is greater, and you just ignore the lesser one. So this is the max metric. And then also think about the discrete metric. The discrete metric, remember the definition of that was all points have distance 1, just no matter what the points are. Unless it's the same point with itself, that's distance 0, because it has to be for the positive definite. But all other points have distance 1 apart from one another. All right? See if you can think about it. So your answer shall be some kind of shape here, which defines actually where is the metric, or where's the ball, and then some other kind of shape apparently here, and then some other kind of shape here. See what you think. I'll give you a few minutes. I'll walk around and see how you're doing. You might find it easier to draw these pictures around the origin. I don't really care if you want to use the origin instead of some point over here. That's fine. Your answers for these should be different. The shape of the taxi cab ball is not the same shape as the maximum ball. Yeah, that's right. I think this is actually, that is even bigger than the circle. Like this one, for instance, that's taxi cab distance from 1 plus 1, which is this. Anymore? We did, that's good. That's right. Is this the max?
Yeah.
That's right.
This is the one that comes to
Yeah.
Because it's diagonal. It has to be rotated. Because it can only go vertically or horizontally.
Where this,
So if it's diagonal, then it's not.
where's the one?
I don't understand the maximum. Like, wouldn't that also just be a square? Yeah, because if it's the maximum, whether it's vertical or horizontal, then it has to have the 4 points. And I
Square
don't
them,
know
then
what's due to this, because we just press 4 things. Would this also just be a circle?
No, it's gonna be different.
Because it has to have the 4 points, right? Because like the
You mean
X.
those 4 points?
Yeah.
Yes. I think it also has points like here. Because then each of the whole columns that goes to 1. You took the bigger one, so it's still just 1.
But it was, so is it just, yeah, is it just a big square?
Yeah, bigger deal there.
Well, yeah, but that's, okay. I didn't know if it, like, if they were the same, if you just take the.
You just take the maximum, so whichever one is bigger.
But if they're the same, then let's take both of them.
Yeah, the max of 1 and 1 is
Is
1.
1,
Yeah,
okay.
right. Yeah, you never add them together.
Okay. Oh, it must be done.
So,
I have no idea.
Mhm. Think about the max. Mm-hmm. What it is. How's it going? Mm-hmm.
Wait, what is it? Screen. I don't know, I don't know what I'm just. Oh, no, that's.
Yes, that's those 4 points.
One if X and Y are the same,
How
zero
about
if
like,
X and Y are the same. Well, X and Y are the same at the corners of here and here.
What about this one? Both of them.
Yeah, they have to be
one,
one.
so you can just take it.
Yeah, the max of 1, 1 is
Okay.
1. Yeah.
No, we just wanted this point X is the same.
I'll give you another minute and we'll think about it. Talk about it. What do you think about the discrete?
I'm not sure.
So the ball of
What's one?
is everything or nothing.
Right.
You want all the points which are distance less than 1 away from x.
And then
That would be nothing, just x.
But I think
just
that's when you use
just
that as one, as one. Oh wait,
An interesting
one's
ball
good,
around it,
one's good,
yeah.
good one.
And what would be, just to make it interesting, for this one you can draw b of x1 and also draw b bar of x1. That's all points which are less than or equal to distance 1. Those are.
So would that just be the same as the standard but with the closed? No.
Because you're still using the discrete distance.
Yeah.
So what are all the points which are distance equal to 1? Oh, or less. But not the normal distance, the discrete distance. Let's chat about these. I think as I was going around, I saw pretty much everybody came up with the proper answers. Maybe I will start drawing my pictures again. I think it is a little easier to reason these out if you consider x being the origin, although once you do it for that, everything else looks fine. So the DT ball, this is the taxi cab ball around the origin, looks like this. You get, well, actually, what I'm drawing here should really be dotted lines because it does not include those boundary points, but it includes everything inside here. All right. Yeah, you get a diamond type shape. That is, you know, these points out here would be distance 1 straight across, but something like here would be 1/2 over plus 1/2 up. So that's why you get that kind of diamond shape. As I walked around, it seemed like everybody figured that out. That was DT. How about the DM, the maximum metric? That's the one where you look at the horizontal and distance and you just take whichever, you look at the horizontal and vertical and you just take whichever is greater. Now if I start at the origin, I am going to get these 4 diamond points again, but if you think a little bit, you will realize I also get a point like here. This would have horizontal distance 1, vertical distance also 1, and so you take the larger of those is just 1, or anything else in this square. So this is what a ball looks like in the maximum metric. It's a square. I think everybody got that. And then what about the discrete metric? This is a little weird. So I have a, I said let's draw b of x comma 1. So if x is the origin, what did you get for the ball of radius 1? That is to say all points of distance less than or equal to 1. Actually, this is the answer. There are no other points that are distance less than 1 from x, because I said less than or equal, I meant strictly less than in this case, because the discrete metric is defined so that everything is distance exactly 1 away from everything else, except for x itself. So x itself, in this case, that the open ball is just equal to x itself and nothing else, because there are no other points that are distance 1 away from x. And what about the closed ball? So in all of these other cases, in these other 2 cases, the closed ball just looks the same, but it includes a solid boundary line, just the way that you would expect. But in this case, actually, the closed ball looks very different. This is all points which are distance less than or equal to 1. What do you say for this? Anybody think about that and come up with something? For example, is if I consider like a point out here, is that distance less than or equal to 1 from x? The answer is yes. The definition of the discrete metric is everything is distance 1. So actually any other point is automatically distance 1 away from x. And even x itself is distance 0. So actually everything is distance 1 or less away from x. So I would say this is just R2. It's everything, all right? When you take the closed ball, you get everything. When you take the open ball, you get nothing. Unless you're actually, if you're using the open ball of radius 2, like b of x comma 2, is also everything, right? That would be everything is within distance 2 of each other, because they are. But if you take just distance 1, less than distance 1, nothing is less than distance 1, except x itself. All right, you can get different kinds of, different looking balls, depending on which metric you use. It's true. All right, you could also think about balls in that weird function space, although this is going to be quite a bit more difficult to visualize. But if I have, say, this space of all continuous functions from a to b, say that's one of them, f. What does the ball around f looks like? B of f, let's say, comma 1. Just, I mean, it's hard to indicate what role 1 plays here, but this would be all other continuous functions which are distance less than 1 away from f. That means that when you compare the two functions in terms of the area in between them, the total area has to be less than 1. And so this would look, I would say, is all sort of nearby functions, where nearby means the area difference is less than 1. So another function inside the ball could be maybe something like this. Say that's my g. My g is close to f because they are you know, they're not always the same, but if you were to take the integral, all the areas over which they differ, that area is small, less than 1 or less than whatever. All right. It's hard to draw completely. I mean, each point of this thing looks like an entire function, so you can't really draw like a shaded area like we did in these examples. But it's any function whose total area difference is less than 1 from f. All right. Great. Let's try and talk about topology with these things. The basic idea, which will be, you know, again, this is something that you would have come up with on your own, is we'll use the epsilon balls to build a topology. This is just the same way that you make the topology like in Rn or whatever, topology. All right, we want to consider an open set is something where you can build that open set as like a union or finite intersection of open balls. Or another way of saying that is you can around any point in your set, you can make an epsilon ball around it such that the ball is totally contained in the whole set. All right, we're going to use the epsilon balls to build a topology. Actually, more technically, this is a little blast from the past, but we'll define a topology using the epsilon balls as basis neighborhoods, right? Remember, one of the sort of cleanest ways to define a topology is by saying what the basis neighborhoods are. The standard topology on Rn uses Euclidean balls, like actual round balls. But you could have also done it using these other types of balls, right? Using these other kinds of balls. So this is the basic idea. We're going to define the topology using the epsilon balls as basis neighborhoods. Now, there is one sort of technical trick to doing this, or a thing that you need to be sure about. This involves the basis set shrinking property, which we are going to have to talk a little bit about, just to make sure that it actually is going to work for these epsilon balls using the metric. if you recall, the basis set shrinking property is something like, I would typically, if I were using circular balls, it's something like if I have two basis sets which overlap and there's a point in the intersection, then there is another basis set that is contained totally inside of the intersection. We're going to have to show that something like this is true for epsilon balls, but you have to demonstrate it's true no matter what, as long as it's a metric. So using only those three properties about a metric, the symmetry, the positive definite, and the triangle inequality. Can you demonstrate that this whole situation will always work out properly? So I'm going to try and do that. Oh, by the way, this is also a ridiculous suggested math-related name, lemma. They actually said you can name your kid lemma. Don't name your kid lemma. That's my advice. A lemma is like a theorem, but not. Usually we call it a lemma if it's not terribly interesting all on its own, but it's principally used to prove a more interesting theorem. Call your kid theorem instead of a lemma, if you like. This is a way to insult a group of mathematicians, and all you guys do is prove lemmas. Where's the real theorems? Yeah, that's a sick burn. I want to prove a simpler version of this kind of a situation, and then we can actually, using this simpler version, it's not so hard to show that picture also is holding. So what I want to do is just to demonstrate that if I have, say, an epsilon ball around X, and some other point inside of that ball, say Y is over here, then there is another ball around Y, which is inside the big ball. All right? This is just, if you have a ball and another point inside the ball, then there's another ball inside the big ball. All right? Now, this is an obvious fact if you're using the Euclidean metric, because you could just draw the circles and you can just say, I make this circle over here smaller than the big one, and until small enough so that it fits inside. But that, of course, we want to write our proof in a way so that it works for any metric, not necessarily the Euclidean metric. And this is where, where in another metric they might not actually look like circles. They might not look like much of anything, like the discrete metric or like this situation. No picture is adequate, really. But I'm going to use this picture over here as inspiration to write the proof. So anyway, here's the statement of the lemma. It says given X and Y in some metric space, if Y is in the ball around X of radius epsilon, then that's the picture here. Then what I want to say is there is a smaller ball around Y where that entire little ball is inside the big ball. So I'm going to say there exists delta, which will be the radius of the Y ball, with ball Y delta is a subset of ball X epsilon. That's what this picture means. If you have the big ball, there's a little ball inside the big ball. All right? And we have to prove this using only the triangle inequality, the symmetry, and the positive definite. And really, it comes down to the triangle inequality here. So I'm going to try to use this picture as inspiration, but actually not using the picture. You have to write everything out in details using what in this case is important is the triangle inequality. All right? Really, so let's do the proof here. The whole trick is to figure out how to choose the delta small enough so that this ball is actually inside of this ball. That's the idea. How do you decide what the delta needs to be? And actually, it's not so hard. You can take your inspiration from the picture and then try to actually prove it without using the picture. If I were to, so on the picture here, the delta is here, right? It's the little radius. And the big question is how to choose exactly what delta is. The delta has to be small enough that it actually fits inside the picture, all right? I think if you draw this picture slightly differently, so I'm going to draw the picture in a more helpful way, which would be just sort of rotate things so that everything is kind of in line here. And I'm going to make the little ball, maybe, let's just make the little ball sort of as big as it could possibly be, but still fit inside. The point is we need the little ball to fit inside. If it's even smaller than that, that's fine, but let's just make it sort of as big as it could be. Now on this picture, I can label some things. That's epsilon. That's the distance all the way from x to the edge is epsilon. And then we also have the distance from y to the edge. Here's y. Just because I lined it up in this way, that little smaller distance is what I want delta to be. All right? So according to the picture then, we should choose delta to be, can anyone say, based on this picture here, how would I define what delta is in terms of everything else in the picture? What you can use is, I mean, you can use epsilon, and you can also use the metric. You can measure the distance between this or that point if you want to. How do I express delta in terms of the other stuff on the picture? Is it
Epsilon over 2?
Epsilon over 2 is kind of cute, but it's not necessarily halfway. I mean, it kind of looks like halfway on my picture, but that's not. It could be, you know, I could have drawn the y very close to the edge, in which case the delta has to be really small. I mean, it's something about epsilon and something else. I would say, here's a hint. If you also consider this distance, this is why I drew them all on the same line. Can you say what is that distance? Epsilon minus y. Can't do that because y is not a real number. Well, I think maybe I know what you mean.
Epsilon minus delta. Wait, what minus epsilon minus delta?
I'm trying to say what delta is, so you should not say delta over here. Yeah, one minus is a good idea, but really it's something like epsilon minus delta is that. In other words, you could say delta is epsilon minus that. But what is that? You can say, would you say it's however far that is? The distance from x to y? Maybe you didn't want to say that. This is distance x to y, right? And that, you know, the metric, we have to use the metric at some point here because that's what this whole theorem is about, metric spaces. So that's what I'm going to choose the delta to be, epsilon minus distance from x to y, right? And then the rest of the what we're going to do for the proof proper, I mean, this is just like getting started here. This is inspired by the picture, although you can't use the picture to just say, well, if I choose it that way, then obviously this circle is inside of that circle. This is not good enough because your argument needs to work for any possible metric, which means we have to describe all of this in terms of the triangle inequality and the symmetry and the positive definite thing. So we should choose this delta. And now let's show, given that choice, we'll show that ball of y comma delta is a subset of ball of x comma epsilon. And the way to do that is you choose some point in this set and you show that it's also in this set. That's what I'm trying to show is a subset inclusion. So I'm going to say choose some point in the set on the left. That is some other point in the little ball. I'm going to call it z. I'll choose some z in the little ball, b of y delta. And then we have to show that z is in b of x epsilon. All right? So can we say, and hopefully this will somehow involve the triangle inequality, because that's really the only thing that we have to use when it comes to, you know, symmetry is not, we will use symmetry, although that's less interesting. The triangle inequality, the positive definite actually doesn't really come into play here because everything is going to be positive anyway. The triangle inequality is really what it's all about. But I feel kind of good about the triangle inequality at this point just because I do actually have 3 points, the x and the y and the z. So, you know, maybe the triangle inequality will get me somewhere. What does it mean? So we should, we should say for these things what I know and what I want to show. What do those actually mean? So z is in this ball means, this means, can I say i.e. z is, no, what that means is the distance from y to z is less than delta. That's what it means that z is in the delta ball. And what I want to show is that the distance from x to z is less than epsilon, because that's what the epsilon ball means. All right, the distance from y to z is less than delta. Could I write that? So what we know, this is really just a matter of sort of putting together a bunch of ingredients. Can I say the triangle inequality says, you know, about x and y and z, it says distance x to z, distance x to y plus distance y to z less than, no, greater than or equal to distance x to z, right? I'm going to start with the distance x to z. I'm going to write it the other way around. Is less than or equal to, by the triangle inequality, distance x to y plus distance y to z. Now, what can we do with those things based on what we already know? Well, we know distance y to z is less than delta. And in fact, delta is given by, you know, I said up here, delta equals epsilon minus d of x comma y. So where I see distance yz, using an inequality, this thing is less than, well, maybe I'll just write delta here. Because it says up there, distance y to z is less than delta here. And then what about distance x to y? What do we know about the relationship between x and y? That's just that y is inside the big ball, which is radius epsilon. Sorry, I know it's time to go. We're almost done. This is epsilon, all right? Because y is inside the epsilon ball. That was our assumption from the very beginning. But now I'm just going to plug in what is delta. Delta we had decided was, this is epsilon plus. Remember, delta is epsilon minus something I don't like about this. Oh, sorry, I did not mean to do that with the dxy. Can I leave this? It wasn't incorrect, but it's bad for the proof. I leave this as a dxy. Plug in delta equals epsilon minus dxy, and they cancel. That's the point of this. The dxy's cancel. Isn't that nice? Another thing you didn't expect to happen in the topology class. Two things canceling because it was a minus. That's like a, reminds you of your youth, right? Anyway, we get dxy, if you read this all the way across. And, sorry, one technicality. Where I said less than or equal here, I should have said just straight up less than, because d of yz is straight up less than delta, not less than or equal. And so when I read this all the way across, it says d of xz less than, not less than or equal, actually less than epsilon. And that's what we wanted to show up here. D of xz is less than epsilon. It all works out using the triangle inequality.